solutions to our composition of functions practice. This is our first grade 12 topic in functions. It's not review like some of the other ideas. And there's at least one quite challenging idea, I would say, embedded in this section, and some quite doable ideas. Now, we went over the examples in class, but I know that we had a few absences in these last few days, so I think I'm going to go through them anyway. So if you want to get straight to the answers to the exercises, you can skip a little ahead in the video. All right, so I think I'll just go through a few of these examples though. Okay, so composition of functions implies that we're putting a function as an input of another function instead of a number or a variable inside as an input of a function. We're going to put another function inside. And that has a certain appearance. It could either be written like so, where we have a regular g function, but inside we'll put an f of x, or maybe an f of 2. And we're going to get to this notation in a second, which can look a little funny. Looks like I might need to focus here. All right. So I'm going to go through an example, and hopefully that helps make sense of some of this stuff. All right, so we've got this statement g of f of 2. So in other words, the g function takes as an input the value f of 2. All right, now we have a couple of different ways we could go about solving that. But what I think might be the easiest thing to do when we have a composition of functions like this is first answer, well, what is f of 2 anyway? F of 2 is the value that we get when we put 2 inside this function. So that means 2 as an input. And it looks like we get 2 times 2 plus 5. We get 9 as an output. So f of 2 is really a funny way of saying 9. So g of f of 2 is kind of like saying what we're really talking about is g of 9. Okay, and what's g of 9? G of 9 is 9 squared. Take away 5 times 9. So that means it's 81. Take away 45. And that's, some number 36? Yeah, I think it's 36. Okay, so I'm going to write that all in one statement. G of f of 2 is 36. All right, now, then we get this kind of funny looking statement. It says fog of fog of negative 3. And what that really is just a funny different notation for saying f of g of negative 3. And you can choose either notation. Sometimes when you're putting a bunch of functions inside each other, like repeatedly, over and over again, this notation might be a little simpler. But I actually think and recommend that whenever we see notation like this, we should rewrite it in this form. And so the first guy goes on the outside, second guy is on the inside. Okay, and then we can proceed as we would have normally. Well, what's g of negative 3? What is that input that's going into f? Well, g of negative 3 is negative 3 squared minus 5 times negative 3. BEDMAS says we need to multiply those together first. So I'm just going to rewrite that here. It'll be negative 3 squared, which is 9. Maybe I'll just write it as 9. Take away 5 times negative 3 is negative 15. So it's like take away negative 15. But so a negative times a negative, that just gives a positive 15. I get the number 24. So that's what g of negative 3 is. So really I'm asking what's f of 24? And f of 24, well, is I multiply by 2, and I add 5. So that looks like 48 plus 5, 53. Okay. Oops. Maybe I should summarize it. So that's f of g of negative 3 is 53. Okay. So I'm not going to go over C and D because they're really repetitions of the same idea. If you got how we did A and B, you could probably do C and D by yourself. You know what? Maybe I'll write out the answer at least so you can check to see if you really get that. So why don't you pause and try C and D, and then unpause and see if you got the right answer. So what do I get in here? F of 1, 2, 7, 7 squared 49, take away 35. 49, take away 35. That's 14, I think. Okay. Citation needed. All right, and G of 7 is the same thing as 14. 28, 33. Okay, I hope those are both right. All right, and then we get a function g of f of x. So rather than receive a specific input that's going into several functions, the question is, can we write a simplified expression for g of f of x? First of all, it's important to recognize that means g, but as my input of g, I'm just going to put the function f of x. All right, well, let's take a look at what that looks like. Well, that's another way of saying g of 2x plus 5. So that's my input to my g function, which means I'm going to square 2x plus 5. Then I'm going to take away 5 times 2x plus 5. So that looked a little funny, but it turns out the execution is not so hard. So g of 2x plus 5 is really, so I'm going to square, so that really becomes 2x plus 5 times 2x plus 5. I'd rainbow that through. I get 4x squared plus 10x plus another 10x, so plus 20x plus 25. And then I'll distribute the negative 5 in as well. I get negative 10x, take away 25. All right, now group like terms. So I see that I've got some x terms here, and I've got some 25 and negative 25, so some variable list terms. And so really g of f of x is really just 4x squared plus 10x, because 25's cancel out. All right. Now, for the heavy lifting. So this, I think, is one of the harder, conceptually speaking, ideas that I think we're ever going to really deal with in Pre-Calc 12. It doesn't seem so difficult when it's said, but there's just like a lot of terminology and deep ideas kind of embedded in here. So we're going to try and go a little slowly through this, and you may need to watch this video a few times to really feel comfortable with it. All right, so to find the domain and range of composite functions, well, that's a little tricky. Okay, so first we're going to read this paragraph, and then we're going to take a look at an example and maybe come back to it, see if we can summarize some key ideas. All right, so what do we got here? We got, so you have got to be careful when determining the domain and range of composite functions, and that's true. So for the composition g of f of x, so f of x is being put into g, the domain is all of the x values that are in the domain of f. So all the x values that are in the domain of the inside function, in other words, such that they give outputs, f of x's, in the domain of g. All right, so I'm going to decode a bit of that. All the x values, all the inputs, or domain of f, such that they yield outputs of f that are in the domain of g. And outputs, of course, we're talking about range. So really, the key idea here is that the range of the inside function, well, really, the domain that gives the range of the inside function has to match the domain of this outer function. And that, I don't know, to me sounds really complicated, and I think it is. It's doable, but just give it the credit it deserves. All right, so we're going to go through a few examples, and hopefully that makes a little more sense as we go through some. All right, so we're going to try and find the domain of f of g of x. Okay. So what I think might be helpful is to start by listing the domain of g of x. What kind of functions can I at least even put into g? I said functions. What I meant to say is what kind of values or elements can I put into g? So I look at my g function here, and it looks like the inputs my g function accepts are, I'll list my domain here. I've got the value 1, 3, 4, and 5. And that's it. And it's a discrete set of inputs. So I'm not going to list it as a range. I don't have the values between 1 and 3. I actually just have 1 or 3, or 5 or 4. Okay. So those are the possible inputs just of the function of g. All right, let's take a look at what outputs we have here. What's important is whatever comes out of the g function. So these numbers are going to go into g. So my inputs are going to go into g of x. And they're going to come out. That's going to be my range. However, then they're going to become inputs of f of x. So these outputs have to become inputs over here. Okay, so the next thing I want to do is just check how many of these outputs of g, how many outputs can become inputs in the first place of f. Well, I can see the output of 3 can act as an input for my f function. And the output of 6 also can be an input of my f function. But the output of 9 doesn't seem to work because I can't put 9 into my f function. 9 is not in the domain of my f function, of my outer function. Same with 12. 12 also is not in the domain of my f function. Okay, so what I'm really looking at then is this idea that the only inputs of g that will give me outputs that fit into the outer function are the values 1 and 3. 1 and 3. Those are the parts of the domain of g that can also be fed into f. So the domain of f of g of x is actually just the values 1 and 3. Because, let's just check here, let's see if we can figure out what's going on. Well, what happens if I put in f of g of 4? Okay, well, g of 4 takes an input of 4 and outputs 9. What's f of 9? Well, f of 9 is not in the domain of f. This doesn't exist. Does not exist. This is no good. That's why our value of 4 is not a possible input of f of g of x. Okay, well, what kind of output can I expect from f of g of x? What can come out of it? Well, if 1 and 3 are my only possible inputs, then I can follow these lines. I can say, okay, well, that means that 1 goes to 3, and then 3 goes in as an input of f, and it maps to 4. And 3, if I put it into the g function, gives an output of 6. 6 as an input of f maps to the value 5. So the range is, well, those are the only possible outputs, 4 and 5. All right. Now we're going to see what it looks like if we go backwards. We're going to look at the domain of g of f of x, which is flipped. So how does it change if we have an f of x on the inside, and now we need to determine the range of the outside? You know what? In the interest of time, I think I'll just write the answer kind of like we did in the last one, and you can check. So you can pause the video now, see if you can tussle your logic through that, see if you can get to the answer, because we did go over these in class. And if you really get what I just said, then you should be able to apply it to C and D. And if not, well, we are going to see some similar questions later on that everybody might need to see these solutions to. So you can check there. And that, in case you were wondering, would be question 3 later on. So you can skip to question 3 if you feel like you need more practice with this skill. All right, so the domain of G of F. Okay, I need to think of that for a second. So outputs of F that match G are going to be 4 and 5. So possible inputs that lead to 4 and 5 are 3, 4, and 6. And the range of G of F of X is, okay, so what kind of outputs can come in if 4 and 5 go in? Well, it's going to be 9 and 12. And the last idea here is, in addition to putting F into G, I could also put F into F if I wanted to. And that's actually as easy as it sounds. The only weird thing we need to talk about is that there's a notation situation going on here. I'm going to zoom in here so we can make sure we can read that. And I'll also focus. So this input of f of x back into the function of f of x could be abbreviated f squared of x. And if I did that again, if I said inside my f function here, put another f of x, I'm going to make them smaller sequentially as I go, with a big fat F outside here. Well, that would be f cubed of x. And that is just a notation. Other than that, this obeys the same rules as any other composite function rule. All right. And we'll see some practice questions so we'll encounter and we can unpack that if that seemed a little fast for you if you missed class today. All right, so we're going to go through some examples. Some practice. Okay, so here are the exercises. All right, so first we want f of g of 2. So first I will find, we want to work from the inside out generally on all of these functions. So what's g of 2? G of 2 is 2 times 2. Take away 1, says 4 take away 1, which is 3. So really, we're looking for f of 3, because what g of 2 is. And f of 3 is 3 plus 5, which is 8. So f of g of 2 is 8. All right, and what about g of h of 2? Well, to start that, we got to find out what h of 2 is. H of 2 is 2 squared, which is 4. So g of 4 is 2 times 4. Take away 1, which is 8. Take away 1, which is 7. So g of h of 2 is 7. All right, h of f of 3, well, I got to find out what f of 3 is. I start from the inside, I work out. F of 3 is 3 plus 5, which is 8. And then I say, okay, well, what's h of f of 3? H of 8. H of 8 is 8 squared, which is 64. So therefore, h of f of 3 is 64. All right. How about g of f of negative 2? So the first thing I like to do is rewrite that, g of f of negative 2. All right, so I got to find f of negative 2. F of negative 2 is negative 2 plus 5, which is 3. So really we're looking for g of 3, which is 2 times 3. Take away 1, 6 take away 1 is 5. Therefore, g of f of negative 2 equals 5. I like to do the same thing with all of these questions. I like as a first step to rewrite these. All right. And so first I'll find g of negative 3. All right, so I'll draw a little arrow there. That's not equal. So g of negative 3 is going to be 2 times negative 3. Take away 1. So that's going to be negative 6. Take away 1, which is negative 7. All right. And then I'll put that into h. So h of negative 7 is going to be negative 7 squared, which is 49. So h, g, or hog negative 3 is 49. All right. Oops, is 49. Didn't realize I was writing off the screen there. Got in the zone. All right, how about h of f of 0, okay? So it's h of f of 0. So the output of f of 0 is going to go into my h function. So first I'll find out what f of 0 is. F of 0 is going to be 0 plus 5, or 5. Okay, so really I'm looking for h of 5. My h function squares a number, squares my input, so I take 5 squared, which is 25. So therefore, h of f of 0 is 25. All right, now we have a function inside a function inside a function. A bit of functionception. All right, so again, first I think it's helpful to write it out. Oh, sorry, it's already written this way. So first I'll find out what f of negative 1 is. And that is negative 1 plus 5. Negative 1 plus 5, which is 4. So that'll work from the inside out. So it's g of 4. That's going to be 2 times 4, 8. Take away 1, 7. 2 times 4, take away 1, which is 7. All right, and then what do I have? I've got h of 7. That's equal to 7 squared, which is 49. So therefore, h of g of f of negative 1, close brackets, is 49. All right, last one. Again, we have a similar type of function, an h function inside the g, which is inside the f. So I think it's good to rewrite it in this form. So we'll start with f of g of h of 4. Close bracket. 1, 2, 3. 1, 2, 3. All right, and so I'll start with h of 4. h of 4 is going to be 4 squared, which is 16. Okay. Then I will move on. I'll say, okay, well, 16, the output of h of 4, is going to go into g. So g of 16. 16 was 2 times 16, take away 1. So it's going to be 31. All right. And then what do I have? I have f of 31, which is 31 plus 5, which is 36. All right, so f of g of h of 4 is all equal to 36. All right, let's move on to question 2. So we have this function. It's a little rational situation going on here. Okay, so we're going to say, okay, well, f squared of 17. So we saw before, that means f of 17. Okay, so to find that, I'll first find what f of 17 is. It's going to be 17 plus 1 over 2. It gives us 18 over 2, which is 9. And then I'm going to put it back into my f function and say, okay, what's f of 9? It's going to be 9 plus 1 over 2. That's 10 over 2, which is 5. All right, so therefore, f squared of 17 is 5. All right, and let's see what happens if we have a f of f of f. F of f of f of 25 is going to be, well, let's see what f of 25 is. That's going to be 25 plus 1, 26 over 2, which is 13. All right, sorry, 25 plus 1 over 2, that's 13. So I'm going to put that into f again. F of 13 is 13 plus 1 over 2, which is 14 over 2, which is 7. And then lastly, I got to do that one more time. and say f of 7 is 7 plus 1 over 2, 8 over 2, which is 4. So therefore, f cubed of 25 is really 4. Funny way of writing 4. All right, so here's a hard question. So first, we're going to find g of f of 1. All right. So first, I should answer the question, well, what's f of 1 anyway? F of 1. F of 1, what's f of 1? F of 1 looks like the input of 1 gives an output of 3. Okay, so really I'm asking what's g of 3? And g of 3. 3 maps to 2 in the g function. Okay, so therefore g of f of 1, well, that's really a funny way of saying 2. Okay. All right, so moving on. Now we have to tackle the domain and the range of g of f of x. Okay. So we're going to start with what kind of inputs could f even accept? F can accept as an input 1, 5, or 9. And when it puts in 1, 5, and 9, it spits out as an output 3, 9, and 15. So the outputs, if I think of these being x's, these being f of x's, outputs of f, I have to ask, well, how many of these outputs match possible inputs of my big G function that they're all getting spat into? If I look, I see I get 3 and 9 match and can map directly into my G function. I don't want to draw too much up here because I have to flip it around later. I don't want to get confused. But it looks like the value input originally of f of 1 and 5 are going to create outputs of my f function that are permitted into my G function. So the domain is really just going to be 1 and 5. And my range is going to be the outputs of those values. So if 1 goes to 3, and then 3 maps to 2 in my G function, and 2 is an output. And if 5 is an input, which maps to 9, and 9 in G maps to 4, and 4 is a range, an output. Okay, we're going to do a similar thing. We're going to look at our inputs of G to start with. 3, 9, and 12 go in. And the outputs of g of x, so if this is x and that's my g of x, when I put an x in, my outputs are 2, 4, and 9. Well, how many of those outputs match inputs of my big f function on the outside? Well, it looks like actually only 9. 9 is the only one. Okay, so the only acceptable input for this composite function that will map consistently throughout both functions is 12. 12 maps to 9 and 9 maps to 15, so the range is 15. And that is it, actually. Okay, last question. I think, yeah, okay. So I'm going to zoom out a little bit so we can see both the graph and the question. Okay, so we're defining f of g, and g. Determine g of f of negative 6. All right, so let's decode this. What's f of negative 6? So here's my f function. Looks like my input is negative 6, or my x value is negative 6. This is my x, or my input axis. All right, and so when I put negative 6 into my graph, it spits out the value 4. I have the point negative 6, 4 here. All right. So f of 6, negative 6, pardon me, that maps as an output to 4. So really what I'm asking is what is g of 4? Well, 4 goes into my g function as an input here. Outputs to the value 4, 2. So my output is 2. So therefore, g of f of negative 6 is 2. Kind of starts to feel like an elaborate shell game after a while. All right, so what about, okay, so now we got to find g of 4. F of g of 4, so we start on the inside, we work out. So 1, 2, 3, 4 here. And we already found that g of 4 was 2. And the question is, okay, well, what's f of 2? F of 1, 2, so then I count down till I get on my graph. Looks like I got the point 2, negative 4 down here. So f of 2 is negative 4. And therefore, f of g of 4 is really just negative 4. Put a little box on that. All right, so the domain and range of g of f of x. Okay. All right, so this is going to be interesting. We're going to use some colors, I think, to help us through here. All right. So, okay, let's start with the domain of g of f of x. So we've got to start with the domain of f. Looks like the domain is all the real numbers of f. Okay, so any number can go into f. And it looks like, actually, any number can come out of f. So I'm going to use green to show my outputs of f. Yeah, so I would map those along. I would say, okay, well, the y values for my f of x function, the ones that can come out, looks like they're all the real y numbers. Now, they need to all be able to go into inputs of g. Okay, so what kind of outputs can go into g? Well, it looks like actually only the acceptable inputs for g are positive numbers, or 0, which isn't positive or negative. So another way we could say positive numbers and 0 is we could say non-negative numbers. Okay, so let's try to write some of this information down. All right, so what do we know? We know for f, we know the domain is such that x belongs to all the reals. And the range such that y is such that is an element of all the reals. G's possible domain is restricted to x is such that, well, x must be bigger than or equal to 0, but we're looking at the elements that are real and within that range, within that domain, I should say. All right, and just for kicks, let's take a look at the range. The range of g looks like it is all the y values that are bigger than 0, and they belong to the reals. All right, so we're going to see how those can help us. So the domain is going to be all of the numbers that can go into f that can spit out outputs that g can accept. This might spin your mind a little bit. All right, so the key idea is the outputs of f need to match the inputs of g. So only half of the outputs of f can be inputs of g. And if we look up on our diagram here, we're going to see these outputs of f, the ones above 0, they can come out and be inputs of g. So only values that come out of f from this point onward in this direction are going to give us outputs that are positive or 0, and therefore be allowed to be inputs of g. Well, that's tough. All right, so maybe I could use some colors here to connect some of these ideas with the diagram. I'm going to zoom out even more. All right. Oops. All right. So this green that I indicated here, that was the range of my f function. So I'm going to highlight that green. My pink here that indicates the domain of my g function, which I'm going to highlight here. And yellow is the part of the domain, pardon me, part of the range of y that is also going to fit into g. So that's actually going to be connected to my g of f of x. That connects my ranges from y that will fit into x here. All right. Now, I don't know how much those colors are going to help. I hope it helps a bit. This is a bit of a tricky concept, as we talked about before. So what inputs give these outputs that are bigger than 0 or equal to 0 for f? So what inputs x's or inputs, I'm going to write that idea down, of f give outputs of f that are bigger than or equal to 0? That's really the question we need to answer. And if we can answer that, well then, because we know all the outputs of f that are bigger than or equal to 0 can be fed as inputs to our g function. So as long as we are only selecting the x's, which give bigger than 0 outputs, then we're fine. Okay, so what kind of x's do we have that do that? Well, it looks like the value x is -2 maps to a value of 0 for y, -2, 0. So that seems okay. And it looks like -3 and 1. So -3 seems to map to a positive y value as well. And it looks like all of these -4, 2, -5, 3, -6, 4, all of these values that are smaller than -2 or equal to it seem to map to values of f's range that are greater than or equal to 0. So it looks like these guys are going to map to this question, which is which x's or inputs of f give outputs of f that are greater than 0. So these, I'm going to use orange to note those x values, which seem to align and match with these y values. So these are the x values here, -2, -3, -4, -5, -6. And they're going to map to these y values that are yellow here. 0, 1, 2, 3, 4. Those are the positive y values. So the answer to what is the domain of g of x, pardon me, what is the domain of g of f of x? Well, the domain is going to be the x values that are -2 or smaller. So x is such that x is smaller than or equal to -2, semicolon, and x is an element of the real numbers. And what range can pop out of it? Well, it looks like the only sort of range that comes out of g, no matter what input it receives, it looks like it can receive all possible inputs from my f function that it could normally accept. So it looks like the range is going to be similar to the range here, which is going to be the y values that are bigger than or equal to 0, such that y is an element of the real number system. And that is for letter C. Okay. I had to kind of highlight that up pretty heavily. So I'm going to see if I can attack D a little bit more succinctly. All right, so what's my domain of G? Well, I already got it listed here. I need the range of G, which looks like all the y values that are bigger than 0. And those values need to be able to map to a value in f. However, f can accept any number for an input. So as long as it can come out of G, it can go into F. So actually, in our D situation, this isn't so bad. The domain is really any value that can go into G, because all those values can pop out in its range and be fed back into our f function as inputs. And that's okay, because our f function accepts any input. It is not discriminatory. All right, so that means that our domain here is, okay, x is such that it was really the domain of G, because feeding it into f offers no additional restrictions. G offers all of the restrictions that it needs. And the range, well, what kind of outputs can come out? Okay, this is actually an interesting question. So G can only spit out numbers that are bigger than or equal to 0. That means the input of our f function, of our f of G, can only be 0 or bigger. So what kind of y values are we looking at here? All right, so we're going to be looking at y values. If this pink is our input of x now, input of f, our y values are going to match are only these ones here, or only the ones from -2 downward. So the only y values that can pop out if you only feed this 0 or bigger numbers are the y values such that y is less than or equal to -2. And y belongs to the reals, which I would say is still kind of tough. All right, so let me know if you have any questions about that. I'll be available for Flex and on Tuesdays and Thursdays after school.